Okay, so we finally reached this point, the very last set of video notes. 12.7, exponential growth and decay. So this again is very similar to the interest formulas we did. Same idea, it's a type of formula that measures how fast something grows or decays, like carbon dating, or bacteria. This is used in a lot of science research. But we need logs to help us solve it, and that's why we're doing it here, is because we might need to use a log to help us solve it. Not always, but sometimes we do. So our exponential growth and decay both of them have the same formula. It's y equals a b to the x power, where again a, b, y, and x all stand for something different. So a is your initial amount, b is your growth factor, and how to tell if that growth factor is going to give you a growth or decay. We use growth in kind of a generic way, but if it's actually growing, b will be bigger than 1. It grows. If b is less than 1, it's decaying. So that means it's shrinking. So it's very similar to, what did we do it? We did it before break, or when we were doing our SBAC review. We were trying to see, is it a growth or decay? If we had 1 point something, then it was growth. If we had 0.92, that was decay, because it was veering off from that 100%. Okay, y, the amount after x time. So that means x has to be our time. So you might have seen this in biology or chemistry. You won't really see this in physics, but you might see it in one of those two, and it's the same formula but different letters maybe. Every subject kind of assigns letters differently, so you might have seen this. It's the same formula, just different letters. If you're in chemistry and you go, oh yeah, but we called it this. I don't care about the letters. I care more that you know how to set it up and solve it, because again, this is more about the solving with logs than the letters in a formula. So we're going to go through, just like last night, we're going to go through one example here and one in class. So 2 word problems on exponential growth and decay. So let's see, number 1. The median price of a new home in Fresno, California, in 1975. This is even before I was born. Was $58,000. In 1990, again before many of you were born, the median price was $113,000. What is the price of a home in A, the year 2000, and B, 1955? So we are pretty much being asked based on on 2 points in time, we're given the median cost of a house. And based on those 2 points in time, can we predict what the average cost will be in 2000? Or how much it would have been back in 1955, 20 years earlier. So when we look at what we have here, we have a spot in time. So that means we have our x. It's just going to be different for each problem. What we don't have is our growth factor. We have a start price, we have an end price, we have time, but we don't have a growth factor, meaning we don't know how quickly these prices are changing. We know they're going up, but we don't know by a percent. So what I'm going to do before I can even answer A or B, so before we even get to that, I have to figure out what is our growth factor. So let's see, I'm going to use 1975, that's my initial year with my initial cost. So 58,000 will be my A. I know that my ending cost, so Y, will be 113,000. The amount of time that's passing, because again, this is from the first one, initially was 1975 to 1990. So how many years have passed? 15 years. And this is going to help us find our growth factor. So a lot of times what they do in research is they pick values that they know so that they can figure out a potential growth factor. So you're going to usually start by using a start point and an end point to find the growth factor and then use it for predictions. So that's kind of what we're doing here. So I'm going to set all of this up into our equation. So 113,000 equals 58,000 times B, which I don't know, to the 15th power. So if I'm solving for B, I need to divide both sides by 58,000. And let's see, those will cancel, so I get 113 over 58. I'm just going to leave it as a fraction. I'll do my calculator work here later. So, to solve for B, do we need to use a log? So, this is where a lot of mistakes happen, is we jump to using logs all the time. We don't need one here. We only have to use logs when the variable is in the exponent. Our variable is not in the exponent. So what we can do here, there's a couple things. You can raise it to the 1 over 15 power, which is like doing the 15th root, so that these cancel, giving us B. And then this is what I plug into the calculator. 113 over 58 to the 1 over 15th power. When we do that, we get 1.045. So when we look at this number here, this is the growth factor that we can now use to help us actually answer the question about what's the price in 2000 and 1955. So if we look at our growth factor, it looks like it's growing at about 4.5%. So if we were to think about how much over 1 it is, it's 0.045, which is about 4.5% every year. So now that we have that, let's go to part A. Let's actually answer our question. A is asking for the year 2000. So again, we're going to start in 1975. So our starting amount is still 58,000. Our ending, we don't know. That's what we're trying to figure out. time. How much time passes between 1975 and 2000? 25 years. And lastly, our growth factor, 1.045. So we can set this up. Y equals 58,000 times 1.045 to the 25th power. And this is all of our numbers are on one side, meaning it's just punch it into a calculator and get an answer. So this top part in green, that was the bulk of the work. Everything else is now just plug it into the formula, type it in, get an answer. So when you type this in, you find that in the year 2000, houses on average were $174,315.20. So that was roughly what they would predict in 1990 what the future 2000 costs were. I can tell you it's much higher now this year, but I don't know if this would actually work. I should try it. Okay, and then for part B, working backwards. If this was still the same initial, so we still have our same initial amount of 58,000. We want to know the ending amount. That's our question. Now time. We're starting in 1975, but we're going back in time to 1955. So how many years, or what would we have to do to go from 1975 back to 1955? We'd have to go negative 20 years. So if you're doing using something to predict what something was earlier in life or earlier in time, just make your time negative and that's okay. And then again, our constant is still 1.045. So y is equal to 58,000 times 1.045 to the negative 20th power. Again, we type this into our calculator and we get that in 1955, the average cost of a house in Fresno was $24,049.29. Okay, so again, we're just looking for, in this type of problem, we had to use two sets of given information where we knew start and end to find the growth factor, and then we used the same start but different endpoints to find, and that growth factor we just found to help us figure out and predict amounts in other years. So we are going to do one more like this where we use our exponential growth and decay, but we're going to be talking about population in California. So this one was housing prices, but now we're going to use it to predict or look at the population growth or decay that's happening in California. So if you have any questions, come with them. Otherwise, we'll do our one last example in class before we start reviewing for your last test and your final.